In the previous lecture, we talked about whether we're using anaerobic or aerobic metabolism in order to meet our ATP demands based on exercise intensity and duration. Now what we're going to switch to is not which pathway we're going to use, but we're going to use what substrate. So are we going to use carbohydrates or fats? I'll briefly bring up proteins before we move on. They add negligible amounts. At rest, about 2%, and you can find these numbers in your book. At high intensity exercise, maybe 5 to even 10% would be on the really high end of energy production used as a substrate. So we're really going to focus on carbohydrates and fats in this lecture. Second point I'll make is that if you'll remember from one of the first slides that I showed in this module that if we're talking fats, right, the only way we can utilize fats is using aerobic metabolism, right? They're broken into two carbon segments that are then converted into acetyl-CoA and then fed in with oxaloacetate into the Krebs cycle. So in this situation, we're only going to be talking about aerobic metabolism, okay? So when we think about substrate utilization, we can think about it in exercise in two ways. One is increasing the intensity of the exercise in, say, for example, a graded exercise test. So if you're in the lab, what we'll be doing is using the Bruce protocol as a graded exercise test. But the idea is that you start someone out at a lower level, maybe a walk at a decent pace, and you increase the pace towards like a walk, a jog, a run, and an all-out maximal effort. And so that's what we're going to look at first, and then we can also just talk about a duration. And that'll be seen in the next slide. So first, let's talk about exercise intensity and substrate utilization. So first, at rest, what I can say is we rely pretty heavily on fat, or as the book uses, triglyceride metabolism, right? And this makes sense, right? And that is because we have lots of it. And so since we have excess fat, we will use that. So at rest, about 33% is used, comes from carbohydrate metabolism, and about 66% from fat. And that's for most people. So rest is 33% carb, 66% fat. Okay? If we look at this increase in VO2 max, or we could say an increase in the speed at which someone is running, again, so a walk, a jog, a run, and an all-out maximal effort, what we'll see that as you increase the intensity, exercise will start to rely heavily on carbohydrates and start to utilize less and less fat metabolism. Right? And this crossover effect right here is considered when carbohydrates and fats equal about 50% of your metabolism. So this graph, in my opinion, shows it a little early. Right? So this one shows it 40%-ish. We'll see where carbohydrate and fat metabolism is pretty equal. When we measure this in the lab, what we're actually going to see is this usually occurs on this side of 50%. So somewhere around closer to 50 to 60% is where we'll see what we term the crossover effect. Again, crossover effect is the idea where fat and carbohydrate metabolism are equal due to an increase in intensity. So what causes this crossover? Why are we switching into carbohydrate metabolism? First is we have an increase in epinephrine, which is the sympathetic nervous system. Right? If we were in England, we would call this adrenaline. Right? So we see an increase in sympathetic nervous system. This hormone, again, what do we know? It increases, ramps up metabolism. It promotes glycolysis. If we promote glycolysis, then we are going to promote more pyruvate being made. It's going to compete with that coenzyme A, more pyruvate than we have fat, and so therefore we're going to start to use more carbohydrate. The second reason is that we have the recruitment of type 2 muscle fibers. more glycolytic enzymes, less mitochondria, and the same idea, right? We're forcing carbohydrate metabolism down the pathway, and that's what is getting into the metabolism, and we're using that. We'll talk more about a couple other reasons here in just a second. So that is intensity. As intensity increases, the reliance on carbohydrates increases. What about in duration? So in duration is, you can think about this as we're not actually increasing speed. So indeed, this is about a low intensity exercise. Again, 40 to 50% of your VO2 max, which is a pretty good jog for most people. A nice little comfortable jog at a low intensity exercise. How do we know it's 40 to 50%? If we look here, our carbohydrates and our fats are almost equal, right? So that tells us if we go back to the intensity exercise here, then that is about that range, about 40 to 50%, right? And so we can see that as the duration of the exercise continues, what we're going to do is we're going to start to rely more on fat, less on carbohydrate, right? Again, this is running at the same speed. So if you could just go out for a jog during your training, you're going to rely more on fat than you are on carbs. One thing I'll note about this is you'll notice that our percentages don't go to 0 and 100, that we really only go from about 50%. It looks much more drastic than it does if you compare it to that previous figure, right? So we go from about 50%, right, to about 60% fat, whereas about 50% carb to about 40% carbohydrate utilization as exercise goes down. So it's not a huge shift, but it is a shift. And we'll talk about why this makes sense here in the next two slides. So first, why use fats at rest, and why should we use fats during long duration exercise? What is our body thinking? So one is the available is how much energy we have available in storage of fat. We've talked about that in our muscle and liver glycogen stores, we have enough glycogen or carbohydrate in the body to do about 2 hours of moderate intensity exercise, right? How much fat do we have? So the idea is presented really well in the book. I love it. Box 3.3-4 in the book. It gives a great example. It says that if we have a 150-pound person who has about 15% body fat, so that's pretty lean, 15% of that 150 pounds would equal to 22 pounds of fat, right? We know that 22 pounds of fat is the equivalent of how many calories? 1 pound of fat, 3,500 calories. So 22 pounds of fat in a body gives us 77,000 calories of fat in our body. That's a lot, if you don't know. So one assumption that we can make, it takes about 100 calories to run a mile. So in this situation, this male could run 777 miles using fat as a substrate, right? So that makes more sense. So there's two reasons. We get more ATP per gram of fat than carb, right? So we get 9, if you'll remember, in fat, 4 in carbohydrates and proteins, and so there's more ATP packed. We even looked at that number that we got much more when we broke it down in the tally. But 2, we just have a lot of it, right? Makes perfect sense. We can either do 2 hours worth of work or 777 miles worth of work with our body stores. So that gives you an idea. At rest, we want to conserve our carbohydrates and use fats, and during exercise, at kind of this low intensity, the idea is we should conserve our carbohydrates and use our fats more. We'll talk about that later. Okay, so then why, if we don't have that many carbs, why do we see in this figure here, in our crossover figure that we talked about, why do we use carbs at a during high intensity exercise? Why aren't we using fats if we're producing more ATP per gram, right? So per gram, yes, we produce more ATP. However, during high intensity exercises where our VO2 is really high, our limiting factor actually becomes getting oxygen to the muscle. When we look at the efficiency of using oxygen, what we can know is that carbohydrates produce 5 calories of energy per 1 liter of oxygen consumed. Again, 5 liters per 1 liter of oxygen consumed. So if we don't have much oxygen, this is going to give us our best bang for our buck, whereas fats only produce 4.7 calories per liter of oxygen consumed. Right? So we're more efficient. We produce more ATP for every liter of oxygen that we consume, which means it's more efficient. Your body's saying, we need to make as much ATP from the limited amount of oxygen we have. Right? If we are limited at the amount of oxygen, you're going to pick carbohydrates every time because of that reason. Right? All right. If we then look at where these sources are coming from, I think this is a great slide which really illustrates a lot. Okay. So during exercise intensities of a low intensity exercise, this is a very easy jog, maybe even a walk here, right? So we know that we're going to rely heavily on fats as our substrate, right? We talked about this earlier, that fats are going to be used heavily on during low intensity exercises. Right, so where do those fats come from? One, we have muscle. We have triglycerides stored in our muscles. We have fat droplets around our muscles. They contribute about 10%, come from our intramuscular triglycerides. We get most of it from blood. So these are circulating free fatty acids that are broken down from lipolysis. So we break fats out of adipocytes and into free fatty acids and then shuttle them in for ATP production. We, again, don't stop using carbohydrates. In fact, we use some carbohydrates. About 10% of our metabolism is carbohydrates, some from plasma glucose and some from glycogen. Right. The idea here at this low intensity, we can preserve and store our carbohydrates very well. At this moderate intensity, 65 is actually a pretty brisk jog for most people, and we'll see that's a nice intensity in the lab. I'll usually try to point that out. Again, here we're starting to use about 50%. So this figure shows it a little bit, depending on who you talk to. Again, about this moderate intensity, we're using carbs and fats to a close degree, but this is a pretty good intensity. So we're using triglycerides. We're getting some from the muscle, some from plasma. Our plasma glucose is providing some, and then the important part is our muscle glycogen is providing a lot. So about 40% of our carbohydrate usage is coming from muscle glycogen. And again, from a physiology standpoint, this also makes sense, right? We're saving an ATP when we use glycogen because that glycogen is broken into glucose 6-phosphate and we don't have to bring in glucose. The other idea is that in the hormone section, we'll talk about insulin and its effect, but we have a harder time getting blood glucose into the cells with exercise training as well, and so we have to utilize the source that we have. So here, about 50% triglycerides, the majority coming from a pretty good combo of both blood and muscle, and then a little bit of glucose, the other 50%, about 10% here. As we go to really high intense exercise, again, we rely heavily on glycogen. Glycogen, as you can see, is the most important carbohydrate store in our body and why it is so important. And so when we talked about carbohydrate loading earlier on in the unit, again, the idea that we can is if we can put more glycogen in, the better, right? And so it is really key that glycogen becomes, at high intensity exercises, predominant. So at this point, 60% of all of our ATP is being generated from glycogen. So you can see high intensity exercises will ultimately cause glycogen depletion. So what does glycogen depletion look like? So here is looking at the duration. So that was intensity. Now we're back in that duration, right? Again, in a moderate intensity exercise, 40 to 50%. think about this as, again, something that you could potentially run a couple hours in at here at the bottom. So at the beginning, remember about 50% from carbs, 50% for free fatty or for fat. At the beginning, coming from a lot of intramuscular triglycerides, we will start to rely less and less on those as exercise goes on, rely heavily on the recruitment of adipocytes, which is great. So we're getting more and more free fatty acids from our fat cells, which is important. You'll notice, though, as exercise earlier, I talked about muscle glycogen at about 85%. We're starting to use it, but what's happening is we're slowly losing glycogen content in our muscle, right? So this is not only indicative of the percentage of energy that we're using from muscle glycogen, but also at the end here, indicative of the amount of muscle glycogen. Indeed, the problem becomes if we run out of muscle glycogen. And what kind of effect does this have? So the idea of performance and muscle glycogen is really important. So we can't maintain a high level of performance if we run out of glycogen. The example that I can give you for this is the idea of if anyone's run a marathon or seen anyone run a marathon or talked to anyone. So if you got a friend, ask them. Say, at what point did it just feel like you hit a wall? Or some people will call it the monkey jumping on their back, right? It's where this, you were going, and then all of a sudden, you felt like you were running in concrete. And that is the idea that in that situation, that is, in general, when muscle glycogen becomes depleted. Okay? When we deplete muscle glycogen, then we really have a hard time using much other metabolism, and that is ultimately going to cause a demise in performance. So maintaining muscle glycogen is really important. However, as we showed in that intensity and as we see here, we are going to continue to use it as much as possible, but as it starts to wane, we only have so much.